and let's save that number that we just had. Okay, now we've got 2 with 3 up arrows and a 4. So this time, instead of increasing the number of arrows, I increased B. Okay, so let's apply rule 3. We get 2 up, up, 2 up, 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 3. And of course, we just did the problem 2 up, 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 3, which is 65,536. Okay. If we continue this process, we only have 2 arrows, so we would mark that down to 1 arrow, and then we would get a new set of parentheses, and we would have 2 up, up, 65,535. And then we would continue and get B to decrease to 65,534. And we would just keep continuing in this process until we get all the way down to 1. Well, that's 65,536 times that we would have to do that. So what we really end up with is 2 up, up, 2 up, 2 up, 2 up, 2 up, 2 up, 2. We would end up with over 65,000 2s that create what we call a power tower. Okay, it just gets really tall very quickly, and it's all powers. There is no way that we can calculate that and get actually a standard number. It would take us like our entire lives to write that out, and I just have until August 10th to finish this presentation. So you're out of luck on that one. Okay. So if that number is not big enough for you, let's do some more up arrow notation. I've got 2 more examples for us. We notice that even small numbers for A, B, and N can lead to exceedingly large results. Okay, so we ended up with 65,000 2s. Let's see what we can get with 3 up, 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 2. So now we've changed A. Instead of a 2, it's a 3. Okay, we end up with 3 up, up, 3 in this case, because after we start subtracting from B, which is 2, we get 1 very quickly, and that ends up reducing to 3 up, up, 3. And then we can apply rule 3 again and get 3 up, 3 up, 3. Okay. That 3 up, 3 inside the parentheses is 3 to the 3rd power, and then we get 3 to the 27th power. 3 to the 27th power reduces to 7.6 trillion. Let's get an even bigger number in here. So we've got 3 up, 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 3. Using rule 3, we get 3 up, up, 3 up, 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 2. And we just calculated 3 up, 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 2 as that 7.6 trillion. So just like in the last example on the previous slide, once we cascade this effect, we end up with 7.6 trillion 3s, all in a power tower. So if we couldn't calculate 2 with like 56,000 2s in the power tower, we definitely cannot actually calculate 3 with 7.6 trillion 3s in its power tower. Okay. So several magic decks were created that could be calculated in up arrow notation. So we saw how large even 2 with 3 up arrows of 4 was, and 3 with 3 up arrows of 3 is. The deck that had been created in 2015 had such recursion that that deck could deal damage amounts of up to 2, where B is 20, and N, the number of arrows, is 408. Holy recursion. We're going to talk now about a very famous number called Graham's number. and it was created in the 70s by Ronald Graham. He ended up writing a paper in 77, and he also actually he was given the title of largest number ever used in a serious mathematical proof in the Guinness Book of World Records in 1980. Eventually, this number has been surpassed by several other ridiculously large numbers, such as Tree 3. But let's focus on Graham's number since it is such a famous example of up arrow notation. Okay. So let's start with G1. Okay, G1 is the very first piece of Graham's number. Okay, it is 3 with 4 up arrows and then another 3. The number we used on this previous slide only had 3 up arrows, and we already ended up with 7.6 trillion threes in our power tower. So Graham's number is going to have a few more 3s to be conservative. Just in G1. That's the beginning portion of constructing Graham's number, which is the iteration G64. Okay, so G1 is 3 with 4 up arrows and a 3. G2 takes G1, and we use that many arrows for G2. And then the number from G2, we use that many up arrows for G3. Then we take that many arrows and use it as the number of arrows for G4. I may have misspoken there. The number G3, that's how many arrows we use for G4. And then the number G4, that's how many arrows we use for G5. And we use this recursion to get the number of arrows, G63, that we use for Graham's number, which is G64. Graham's number is so large that sometimes we don't actually write it in up arrow notation because, as you can see, we haven't really written that many arrows. We just know that they exist, and we don't really take Graham's word for it, but we see what the pattern is. It would just take, more than our lifetimes to write out all those arrows, much less write the number that is actually Graham's number. And just so you know, Graham's number, we said, was the largest number used in a mathematical proof. It was used in a proof of Ramsey numbers, okay, with hypercubes. So let's talk about another way to talk about immensely large numbers, because sometimes even up arrow notation can't express really the numbers we're talking about. Okay, so let's talk about ordinal numbers, and we have Georg Cantor, who first talked about ordinal numbers back in 1883. Ordinal numbers, which sound like the word order, ordinal numbers describe the position of elements in a well-ordered set. And we require that we have a well-ordered set with no infinitely decreasing sequence. So it can be infinitely increasing, just not decreasing. Let's get a quick example here. We have the set E, which is 5, 8, 4, 9, 12. So those elements in the set we can put in order from smallest to largest, and the ordinal that we use for those are 1 through 5, since there were 5 numbers in the set. The smallest number gets 1, the largest number, which is the 5th number, gets ordinal 5. What's so special about ordinals is that they can be used to extend natural numbers. So we can think about numbers that have been extended past what we would normally think as a ridiculously large natural number. After all of the natural numbers, we have the first infinite ordinal, omega. omega, we can have omega plus 1 and then omega plus 2. So we can use a lot of operations that we already used back in elementary school on this very non-elementary type of problem. After we count all the way through the natural numbers, we end up with 2 omegas, right? Omega plus omega, or omega times 2. And for ordinals, we actually write the coefficient after the ordinal. I know it looks a little awkward on the screen, but we do omega times 2, omega times 2, and then add 1, omega times 2, add 2, and so on, until eventually we're adding on a third omega, so we get omega times 3. Now, obviously, I can't go through every single omega, because there's an infinite number of them, but at some point we get to omega squared or omega cubed and so on. We get to omega to the omega power, and we get these power towers of omegas. Okay. So that's our ordinal numbers. And normally when we write out ordinal numbers, when there are ordinals with different exponents, we write them actually a lot like we write polynomials. So we would put the largest exponent first, and then we would just continue down, kind of like we put polynomials in standard form. Okay. Ordinals are useful for what we call the fast-growing hierarchy. Okay. The fast-growing hierarchy is an ordinal indexed family of rapidly increasing functions. So alpha, the index on F, is an ordinal. So alpha can be some natural number or a large countable ordinal. So we can get all the way up to omegas. So we have the function of the natural numbers to the natural numbers, and here is the definition of the fast-growing hierarchy. Okay, so F naught of n equals n plus 1. After that, we have some recursive type formulas. F with an index of alpha plus 1 of n is F with index of alpha, so the previous function of n, and we take n copies of F alpha. So that's what that kind of exponent on F looks like. It kind of looks like an exponent, it's an n. It just means that we're taking n copies of the previous F alpha. Okay, so you can see all of those nested F alphas of n. In the bottom portion, we have F of alpha plus omega to the m power of n, and that equals, again, we're just reducing by 1, and that little n should actually be what looks like the exponent on the previous one, showing that there's n copies of F alpha if m is greater than 0.